Hello, everyone. I suppose that you can hear me. Hello, hello to everyone. And well, I'm Chema Molina. I'm the CIO of Frenetic, and I would like to welcome you to this seminar about magnetic materials, where we will have the pleasure of having you as a guest, Ferroxcube. Well, after this warm reception, I'm going to proceed with explaining how this seminar will be. Well, first, our guest, Ferroxcube, will present the company and news for about 15 minutes. And after that, we will start with a selection of questions that we have that you have sent us previously, and then we will continue with the questions that all of you will ask during the seminar. Take your time and write your question in the Q&A box, not in the chat, just in the Q&A box, please. And well, also during the seminar, you will see some surveys that we will launch. Now, advertising alert, most of you already know that in Frenetic, we take care of designs using high computing technology, but probably you don't know that we have built a factory for fast samples. Well, and as a reminder, I have to say that we have some coming events and one online demonstration, the 2nd of June, and a presentation about full bridge transformer design in the PELS Association. And well, now I'm delighted to give the floor without any further ado to Helge Peters. Well, Helge Peters is a very young man of 52 years old. He studied electrical engineering and he has been in Ferroxcube for more than 25 years. Currently, he's the sales director in Europe and the director of all the European legal entities of Ferroxcube. Then please, I will give the word to him. Yeah, I think that you're there. Hello.
Now I can unmute my microphone. Thanks a lot, Chema. Thank you. Yes, Oscar, could you please start sharing your screen so that we can go through the slides quickly?
Okay. 1 second, please. Something's going wrong.
All right, that's sharing. Okay.
Okay, now it is.
Okay, perfect. So we switch to the agenda. Next slide, please. So today is our first part, and hopefully we will have a second and a third one. But the part today is focusing on our low frequency powder grades. I will have a short company presentation. It's just 3 slides to get everybody familiar who is not yet about the Ferroxcube company. Then I will hand over to my colleagues and then we go through the design parameters, material overview, low frequency power grade highlights, and then a short summary. Everything should be roughly 20 minutes, and then we will have time enough for your questions, which we would like to help to answer. So just a quick look to the Ferroxcube milestones. For those who do not know, The name Ferroxcube was born already in 1941, when Philips, at that time, the famous Dutch company, has invented the industrial production of soft ferrites. And at that time, we got a patent, which you can see on the right side. And we call this material Ferroxcube because of ferrox for the iron, the ox for the oxide, which are 75% of the content of our material, and the cubic structure, chemical structure of the material. So until 1998, several smaller factories were established all over the world, Spain, in Hamburg, in US, and in Taiwan. And in 1998, we started the still existing huge factory in Poland and tried to put everything together there. In the year 2000, Philips decided to sell all the passive components activities, and we were acquired by Yageo, the worldwide largest and biggest producer of chip resistors. In 2001, we relocated our Taiwanese factory to China in Dongguan, where it's still running. And finally, in 2017, we have been acquired by the Chilisin Group, who has a financial relationship to Yageo, so it's not a completely new owner. And that's why we are still 100% owned by a Taiwanese company, but being a 100% Dutch and European entity. So for the next slide, you will see that the capability of our two existing factories. We have 700 people in Poland. We have there the ferrite core production, but also very important, the powder preparation, powder production, as well, of course, the development here. The capacity at the moment is 5,500 tons per year, and for the powder is 12,000 metric tons per year. The capability, I do not want to go through it here. It's everything you can think of how you can, let's say, work and form and sinter ferrite cores. Dongguan factory is 500 people working size. They do only the ferrite cores. They get the powder from Poland, and the 5,000 tons per year is actually their capacity. You might recognize there's a difference in the powder maximum capacity and the sum of both Poland and Dongguan factory production capacity, but there's a reason behind. At this moment, we are planning to have a third factory in mainland China to increase our capacity strongly. So it will start most probably next year with half of the capacity of those factories you see here, and then ramp up to be even bigger. So we have big plans to increase our, let's say, capacity. Just my last slide, please, Oscar. This is the global footprint we are talking about. You see the two factories, one in Skierniewice in Poland, which is about 1 hour drive from Warsaw in distance. We have one factory in Dongguan, and then you see a lot of, let's say, service and sales centers. I just want to draw your attention to our market situation. So we are by far the market leader in Europe with 48% of market share. That's traditionally related to the old Philips heritage and history. Almost the same we have in the USA, and we are digging in Asia to increase our, let's say, capacity, let's say our market share over there. That is also why we are going to have a third factory soon. So that's my short introduction to the Ferroxcube group. And now I would like to hand over to my colleague, who is our global R&D head. He has, let's say, his expertise in material and powder development, and a special focus there. He has his PhD in material engineering, and similar as me, he's more than 25 years in the company, and with the age of 57, he also spent almost half of his life in this company. I'm not sure if this is good or a bad sign for both of us, but anyway, so give my, let's say, Dr. Dietmar Holz, please take over.
Okay, thank you, Helge, for your nice introduction. And
welcome.
Hello? Oh, yes. Now? Can you hear me now?
Yes.
Okay, thank you. So Helge, thank you for the nice introduction and good evening to everybody. Nice that we get the opportunity to talk to you. Maybe we will exceed a little bit the 15-20 minutes, but I hope the interesting last slides will compensate for that. Today, I'd like to explain you a little bit our ferrite materials that you are using to design soft magnetic functions such as inductors, transformers, or choke filters. But first, let's go one step back. What is magnetism? This is a very essential question to understand the materials. Magnetic moments arise from electrically charged particles like electrons. Unfortunately, at least in the sense of our task to design magnetic materials, the majority of these magnetic moments are compensated and cannot be used. In our periodic system, there are only 3 elements or only a few elements with unpaired electrons like iron, cobalt, and nickel. The most common and cheapest element for magnetic applications is iron, of course. However, iron as a metal exhibits several structural drawbacks in comparison to much more complex structures, as is shown here in this slide. Ferrites are ceramics, specifically oxide ceramics, with a cubic closed packing of oxygen ions with positively charged metal ions sitting on positions between the oxygen ions. The positioning of these metal ions follows very strict rules according to ion radius, valence, over lattice occupation rules, but offers as such conditions of very high stability so that we can use these specific structures. The great advantage of ferrites versus metals is that the electromagnetic properties can be tailored in a very wide range by the chemical composition. Background is that the overall magnetization M of a ferrite material is the difference of the magnetization of 2 sublattices A and B. And by adding a non-magnetic element like zinc in one of the lattices, the overall magnetization gets improved. In that respect, parameters like iron content, the ratio of manganese and zinc, or nickel and zinc, are used to design ferrite materials with specific properties like Curie temperature, permeability level, saturation flux density, and others. Other important parameters to tailor the properties of ferrites are temperature and atmosphere during sintering, the final products. They impact the microstructural characteristics such as grain size, porosity, and grain boundary thickness, but also the magnetic defect structure, meaning where exactly the metal ions are located in the crystal sublattices. One important remark, all ferrite materials exhibit anisotropic properties, meaning that the properties are strongly temperature dependent. You need to memorize that materials are generally designed for specific temperature ranges, and leaving these ranges may lead to deterioration of the properties. Next slide, please. This slide describes a basic principle of power designs, which is for sure known to you, meaning that the amount of power that can be transferred to a ferrite core is proportional to the frequency F and the flux density B to the power of 2. However, we also need to recognize that such power transfer causes loss due to certain mechanisms, which I'm going to explain. Hysteresis loss is quite obvious, knowing that the material magnetization follows a hysteresis loop. A small magnetic field strength, H, results in a small magnetic flux density in the material. A higher magnetic field strength in a higher flux density, but also in a much wider hysteresis loop, which represents the loss. It is therefore, the loss is proportional to the frequency and B. Next slide, please. We already learned that power loss depends on frequency, flux density, and material temperature. As a result of the application conditions, the more harsh the application temperatures, the higher the temperature rises in the core. However, in addition to the already mentioned hysteresis loss, there are two more loss mechanisms. Eddy currents occur due to electric current induced by a changing magnetic field, according to Faraday's law of induction. Eddy currents flow in closed loops within ferrites, in planes perpendicular to the magnetic field, and therefore counteract the outer magnetization, causing loss. Residual loss is linked to the resonance frequency of the ferrite core. The closer the application frequency gets to the resonance frequency of the material, the higher the loss. Next slide. This is the last slide of this subject about material design. It summarizes the impact of certain loss mechanisms on applications. Hysteresis loss is proportional to B and F and dominant for applications below 100 kilohertz. In favor of low power loss is a large grain size and a low anisotropy of the material. Eddy current loss is proportional to F and B, rose to the power of 2, and gets therefore dominant at higher frequency and flux. Additionally, eddy current loss increases with larger core cross-sections, usually expressed as the effective area AE. Design parameters to reduce this type of loss are smaller grain size surrounded by highly resistive grain boundaries. Residual loss is inversely proportional to the resonance frequency and also to the permeability of the material, and increases with B to the power of 2. It gets dominant at high frequencies and high flux levels. Therefore, increasing application frequencies require a reduced application flux density and smaller cores to avoid extreme power loss. The next slides will be presented by my colleague David Castillo, 45 years old, electronic engineer with more than 20 years experience with Ferroxcube in specific positions such as factory engineer, quality manager, and for the last years as a field application engineer. Thank you for your attention.
Now, okay.
Yes.
Sorry, I was muted, so and I was trying to enter and I couldn't. Good evening, everybody. Thank you very much, Dietmar, for your introduction. I'm going to present you our spider chart for power materials. In this chart, we show all our more newest material and our different working directions. We have a similar chart for ME materials, but this is not the intention of this webinar. So yeah, first let me introduce how we name our materials, because yeah, perhaps there are somebody that are not used to it. And the first digit in our materials refers to the composition. If it is a number 3, it is a manganese zinc material, and if it is a number 4, it is a nickel zinc material. Then we have a letter. It can be in this chart C or F principal, because they are intended for power, or the F, and this refers to the family of materials. The F remains to the frequency materials, while the C remains to the power materials. We have different letters for other applications. So in this chart, we show our different working directions. In the top right part, you can see the white temperature materials, 3095, 3097, 3095A, and 3095F. As you can see, the digits, the last digits on the family name are the different material that are intended for different application. I'm not going to enter in detail in any of them, as later Marcin Królak will show the characteristics of the most advanced ones. Then in the bottom right part, you can see the materials that are intended to work for a specific and optimized temperature. It can be 25, 60, or 100 degrees. And on the top left part, you can see the frequency materials. There we have 3F36, 3F46, 3F56, and the 4F1 and 4F1A materials, as well as the new ones that, as you can see, are with an orange circle, and it make the idea that they are the new materials that are available but are recently launched to the market. And in the bottom left part, we have also the high DC stability materials, where you can see 392 and 392A and 399. And they are intended to work at different temperatures, also as well as the bottom right part. As you can see, we have too many materials, and all of them are intended to work good or better for what they are designed. So when we choose a material, we have to select the proper one, the one with the best and the accurate characteristics. So now I will leave Marcin Królak to introduce some of them. Marcin has a Master of Science in Electronics Engineer, and he is working for Ferroxcube for more than 20 years. And nowadays he's the product manager in the Poland ferrite factory. So I will leave the control to him.
Hi, David. Thank you for your introduction, but please don't leave me. Stay with us. Yeah, I will be talking about our power materials. Historically speaking, we started with the materials which were designated for one temperature. That was 100 degrees, because that's usually how the application have been working. And then somebody who is with us long time ago can recognize the materials like 390, 94. We on this slide presented the successor of those typical power materials, 396, but we consider even 396 as a mature and very good established material on the market. Then comparing to this, we established 398, which is even better than 396, but please remember this is still material designed for one temperature, around 100 degrees. Next slide, please. Yeah, then with the time we realized that not all applications are working in the same and stable temperature. So we started to think, what can we do to develop the materials which can work in a varying temperature conditions? Then the idea of 395, 395A and 397 came. These are a group of the materials which are pretty similar. The characteristic for them is a relatively flat power loss versus temperature curve. There are nuances between them. 395 is designed for a little bit lower temperatures, 397 for a little bit higher temperatures. 95A is an upgraded version of 395 with a curve a little bit lower than the rest. But in general, all those materials are something which is right now a standard on this market. Yeah, and that's it. Then next to that, next slide, please. Yeah, next to that, we have noticed that not always the power losses in the ferrite are a dominant factor. Sometimes gaining a few milliteslas in the ferrite is also an advantage. So we developed the material in the direction of getting a maximum saturation values. And this is the group like 392 and 392A. As you can see, the power loss curves are not perfect, but the BSAT we got on those materials is 20-30 points better than on the typical power materials. And that applies also to BSAT in 25 degrees or 100 and 140 degrees. So this is the group designed specifically for inductors or multi-gap cores and these kind of things. Next slide, please. Yeah, and then there is also a possibility to manipulate with the ferrite, because what I wanted to say is that perfectly everybody would like to have a ferrite with high permeability, high BSAT, best power losses in all the temperatures, but this is typically not possible. We always trade one parameter for the other parameter. So the 3C99 material is an example of a niche material designed for 200 degrees. So, for example, in the applications that are working in the, I don't know, coal mines or in a very heavy temperature conditions, difficult to find the semiconductors following it, but sometimes you can imagine that the ferrite can be separated from the semiconductors. What this material is maybe showing is that we have a design possibilities with the materials to design whatever we like. We can go with the ferrite to the highest temperature. We can go with the ferrite to the higher BSAT levels. Depends what is the customer needs. But please notice this is the material specially designed for heavy working temperature operations. Okay, next slide, please. That will be for my friend and colleague, for Oscar, to comment. So let me introduce Oscar. Is the engineer of electronics operating in Madrid. He's in Ferroxcube since, I would say, something like
26
years. Yeah.
26 years.
Okay, Oscar, please continue.
Okay, so I would like to switch a little bit the way of the presentation. Now we will talk a little bit more about the applications and real functions. So first of all, we have spoken about a lot of different materials. Now everybody would wonder which one should I use for my application. In that sense, we would say that it depends on basically on your requirements, but the main functions should be defined by these 4 working parameters. So whenever you are looking for a low loss transformer, for example, with the lowest loss working at the 100 degrees, I would suggest to go to 3C98. This will exhibit the best performance whenever you can keep the conditions stable at 100 degrees. Then, okay, maybe you don't have the possibility to keep that good temperature control. Then the best candidates can be 3C95A or 3C97, depending on your temperature range. This can be for portable appliances like laptop chargers or low temperature operation, or if you are working on automotive, 3C97 would be a great candidate with very good low losses in the range from 60 to 140. Then, if you are working on a very high temperature, so for example, close to the on automotive or on harsh environments, then go to 3C97 because it still shows very low losses even at 140, or even as Marcin mentioned before, go to 3C99 for the low temperature, for decreasing power losses up to 200 degrees. And finally, because this was basically for transformers, but in case you needed you have to build an inductor, a high current, high saturation inductor, then go for 3C92A or also 3C99. 3C99 will have extremely high saturation at increase in temperature. If the temperature is in the range up to 140 degrees, then 3C92A would be a perfect candidate. Next is, I would like to talk also about how to design your components. We have basically some soft ferrite design tools which were developed, I would say, roughly 15 years ago or even longer. Unfortunately, we don't have the tools to update them. So let's say they are as they are now. In many cases, they can still be used. On the other hand, we have defined our Steinmetz coefficients, which are available on an Excel file, and you can download them from the web. And they are constantly updated. Whenever we develop a new material, it takes some time because we need to make all the calculations, but you can use these Steinmetz coefficients, apply them on this formula, and then you can get let's say, an approximation to the power loss expected for that specific conditions of frequency, flux density, and temperature. Let's say the spreadsheet where you can download them from will also use them on the formula. So it's either you can paste them to your own calculation tool, or you can directly use them on the Excel file. And also we have planned to make a revision of the soft ferrite design tools to work online, but this is still in progress. It will take some time until it is released. And then we have been showing a lot about the material properties, but when we talk about materials, we are not talking exactly about the products. What happens when we have a product? So let's say common shapes will have some impact with for example, concentration in the corners of the flux concentration in the corners that will lead to higher flux density and therefore higher power losses. We will have also stress on the contact surfaces, which are ground. Again, this will damage the microstructure that Dietmar was presenting, and this will again lead to increased power losses. And then we have, of course, we try to minimize it, but we have some variability in production. Again, will lead not to lower power losses, but also to increase the power losses. And another effect that we see not on every product, but only on those with a very large cross-section, when the effective area becomes larger than, let's say, 250, it becomes really significant. We start to have eddy currents. Eddy currents, as Dietmar explained before, are due to the resistivity of the material, that that the magnetic flux will induce current inside the ferrite core, and due to this resistivity, this will increase the temperature of the core, and this temperature will be again power loss. And this effect has two negative impacts. One is the power loss, but also that this minimum sweet point of a power loss, minimum losses, will shift to slightly lower temperature. All these factors will lead to the fact that the material specs are not identical to the product specs. So we need to apply some correction factor. But in any case, we have our materials and products all are specified according to what we can fulfill. And yeah, I would say this is all from the presentation point of view. Now we would like to give you the opportunity to ask some questions, and we will also try to answer the questions that you placed when you subscribed to the webinar.
Okay, Oscar, thank you very much. We have a lot of questions, and then we are trying to move forward. Well, thank you all of you for being here until now. Now I'm going to launch one of the surveys while we are preparing next question. Well, first question, and then. Well, I think that you can see my screen, right?
Yes.
Can you see the presentation?
No, we see only your nice picture.
Okay. 1 second, just I'm going to share the screen. Well, now we are going to follow with the questions that we have here. I think now you can see my screen.
Yes. Now we have the presentation.
Okay.
Yes, now it is the presentation.
Yeah. Well, now the point is that we have here some experts in this industry, great experts in the magnetic design materials, and also we have included some, I mean, like Oscar from Ferroxcube, that is expert in design also the applications, but also we have included Lucas Nicieza, one of the power electronic engineers, the power electronic manager in our team, to answer some of the questions. Then I will allow them to talk and to switch on their cameras. And now here is the first. I will try to answer the question as fast as possible, because we have plenty of them, and I think that a lot of people is very interested in the question. Then please try to answer just in a few seconds, and then if there is additional questions, we will try to answer by email later. Okay, then this is the first question. Is there any work being done to characterize losses across static cycles as well as high frequencies?
Well, I could say yes, that if we talk about the core, there are several studies, like there are models like improved generalized Steinmetz for calculating the losses in the core for any type of waveform. So there you will have into account the duty cycle.
Okay. Then I'm going to move to the next one. Which material and new core shapes are there for GaN applications?
I would say that for GaN applications working at very high frequencies, let's say we will dedicate a specific webinar next time. But we have some materials like 3F36, 3F46, which can work nicely up to in the range from 400 kilohertz up to 2 megahertz, and also we are expanding the range with 3F56, where it can switch, it can work up to probably 4 or 5 megahertz.
Oscar, if you think about the core shape, what do you think? I would say that if we are with GaN application that we are running at very high frequency and you need very, very high power density, then we will need a very low profile, right? Like the core shapes in the GaN applications could be very low profile, especially for planar transformers. What's your opinion on that?
Yes, I fully agree with that. Most common will be planar magnetics, where because you don't need to have so much space for windings, because normally just one or a few turns will be needed, and then you can have also a very nice large surface for removing the power loss from the core.
Okay, then move to the next one. What are the different ways to increase shock and vibration performance of ferrites when designing transformers?
Okay, I would like to answer this one also. Let's say the most important factors from the ferrite point of view is to avoid the large edges and also to increase the radius in the corners. So that we have reinforced angles on the ferrites. That's from the ferrite point of view, but we should think also from the assembly point of view. So what kind of clamps or what kind of potting materials are going to be used when you are making the encapsulation of the transformer.
Okay. Next, does Ferroxcube provide cores with the possibility to build magnetics using distributed air gaps?
Yes, actually, this kind of distributed air gaps is not new for us. We have, let's say, customized products in mass production running, let's say, on a high level. They are done in Poland, but recently we have established automated production line for some high runners, multi-gap cores in our China factory, as I said, for instance, for E71 core sizes like that. And then we glue and the FR4 or alumina distance plates in as well. But what we can also do, of course, is we can offer all the ferrite plates and blocks for the customers to glue the products themselves. So the answer is clearly yes.
Okay, thank you for the answer. Actually, we need some new distributed gaps now. Well, in terms of losses, PV loss and Steinmetz coefficient, are these good enough for loss calculation of magnetic component using in DC-DC converter?
Okay, well, let's say this is, you can never say that they are good enough for all conditions, but I would say at least they can give you a very good hint of what will be the typical size and the windings for them. Nevertheless, this means that you will have to make some trials and probably make some iterations. In this sense, Frenetic, of course, can help to make this step a little bit faster.
Well, thank you very much. Well, this is the reason that the main reason we create our technology. That well, we don't. I think that this coefficient and this way to calculate the losses is not bad. But when you are going to the limits, having technology to help you to find the optimum values, I think that it helps a lot. Well, next one. Could there be more vertical core geometries for transformer? Well, I think this person is asking for customized or more different shapes?
I mean, I have to say that in the meantime, about 70 or 80% of our business is done by customized products. So we do not need to check and let's say only the existing products, but they do not should not hesitate to ask us for customized products. And yes, we can do this. Of course, there are at this moment limitations to the equipment we have. We have some filling, let's say, distances in our press machines, but from the theoretical point of view, we do not have any limitations here. It might need some more investments. At the moment, with the equipment we have at this moment, I would say we are something like 150 millimeter in height. But yes, we are looking forward to support with customized designs also in this kind of length and height shape ratio.
Well, just to add some comment, most of our, I mean, I would say 40% of our current designs are using custom core, and it's very common. What development will we see next in terms of size reduction and thermal improvement? I think that this is supposed to be related with the cores.
Yeah, I would say this question, I would link it very much with the very first one that we discussed about the gallium nitride switches, because it goes in the same direction. So to go into size reduction, we should normally increase the switching frequency, which goes in the direction of using higher speed switches, and also for thermal improvement, what we see is that it is becoming more and more popular to use planar magnetics, where it is very easy to attach a large heat sink, and then you can easily remove the excess of heat from the component.
I would like to ask Lucas what he thinks about moving all the design to planar, to move more design to planar solutions in terms of high power.
I like it, but then in planar, there are, let's say that if concentric magnetics have problems, planar are a complete, not so well-known field. So, but I think it's where we are going now, because as Oscar said, we need higher frequency, we need lower profile, and we need much better cooling there. So yeah, planar definitely, we are working a lot on that, and it's the way we have to go.
Okay, thank you. Well, let's try to move fast. What will be the best magnetic solution for a 200 kilowatt wireless bus charger? Any comment?
Yeah, I would say that for this application, what we would recommend is to use as material the 3C95, that it is used for a wide temperature range, and for the shape, of course, large tiles where we can cover the large windings that are needed, and so that we can close the magnetic circuit better. So definitely okay. Large tiles in 3C95.
Thank you, David. I will launch another survey, and in the meantime, I would like to know if our friend Marcin is still there. Marcin, are you there?
Yes, I'm there. I'm typing the answers for the questions, if you have not noticed.
They don't allow you to answer anyone.
Okay, I answered at least 5 of the question and answer in the meantime. So please tell me.
No, I mean, it was just a joke, just while we are doing the survey. Well, in the meantime, launch the next question. Does core size only depend on the size of the application? Well, it's more a philosophical question.
Okay, let me answer that. Yes, core size depends on the size of the application. No, but to be honest, there is no limitation in the core size for a ferrite physical. You know, we are doing special ferrites. We are doing also 500 millimeter cores. So everything technically is possible. Of course, what limits us is usually economy. So when we are talking about typical ferrite applications and the ferrites which should not cost too much, we are talking about reasonable money. Then we are talking about the cores below 100 millimeters. But if somebody wants, we can do better. We can do bigger. It's enough to look at our special ferrite portfolio.
Okay, thanks, Marcin. Could you comment on magnetic component mechanical structure or single core versus multi-core magnetics for a very high frequency application? I think that this is very common. Who is going to answer?
Okay, I would like to answer. This is not so easy to, let's say, there are two possibilities when we are talking about multi-core magnetics, and especially when we are talking about very high frequency applications. There are two possibilities. We can split the core in the direction parallel to the magnetic field. So let's say slicing the core in several sheets, like it is done with laminated steel, for example. This would help to reduce the eddy currents and also the skin effect on the ferrite that I was commenting before. That ferrites, especially manganese zinc ferrites, suffer from eddy currents. So this would help to reduce the core losses. Another possibility, another way to see multi-core magnetics is to, in the case where you have high current inductors with large gaps, you can make the gap divided in smaller parts. So using a so-called multi-gap solution. Of course, this is a real improvement, not only for high frequency, but for, I would say, for almost every frequency, because when you reduce the fringing flux on the gaps, you will strongly reduce the losses on the windings, because there is no field through the winding, and that will, of course, improve it.
Okay, thank you, Oscar. Next one. What is your roadmap for materials development that could enable high power, more than 1 kilowatt, and at higher frequencies than 1 megahertz? Hello?
Please unmute Dietmar, because I see that he's trying to speak.
Dietmar is trying to talk, but Dietmar is muted.
Okay.
Question.
Now we can hear you. Please start again.
Okay, this is a very nice question, and we have already given part of the answer in the spider diagram. We are designing materials for high frequency, but today the focus was on low frequency materials. So our proposal would be to set up a new webinar for high frequency, where we could present our materials 3F36, 3F46, 3F56, and also we have a power grade in nickel zinc 4F1.
Okay, thank you, Dietmar. I think that there are more questions related with this topic. It's a very interesting topic, and then we can contact the interested people to talk a little bit more about this. Something related with flyback. High voltage secondary in a flyback transformer B1 first to reduce leakage. I think that have no too much to with the core, but someone want to comment something?
Yeah, I would say that if we talk about a high voltage secondary side transformer, I would worry more about the self-capacitance of the winding. So what I would do is to put it in the inner layer, do set winding transformer to reduce the parasitic capacitance, and then put a triple insulated wire in the outer layer. We could reduce the leakage inductance by doing more interleaving, but if we are talking about a very high voltage transformer, then we will have problems, or we will need a very big window area for the insulation. So yeah, you could have reduce leakage inductance with a split winding, having inner layer, then primary side, and then the other half. But yeah, I would take a lot of care about the self-capacitance of the secondary winding.
Okay, thank you, Lucas. This is something that I think that I have asked in the past to Dietmar and Oscar, and I think that is interesting to explain to people. How does the Ferroxcube measure the data to form, to create a data set?
I can reply also. Normally, what we do, we always measure in the same piece, and it is a standard 25mm toroid. This is because we want to compare one material with the others, and also within one material, one batch from the other, and with the spec. So it is the standard way to do it. For the high frequency materials, we use, instead of the 25mm toroid, a 14mm toroid, but this is the shape we use to make the data sheets.
Okay, thank you. In which direction is development for high saturation flux density ferrite cores product?
Okay, I will answer that question. Generally, we need to understand that the flux density at 0 Kelvin is the highest, but very much dependent on the composition. That's one point, but having a low flux density at 0 Kelvin does not mean that at 100 it is better or worse than another material, because at the end it degrades mostly linearly from 0 Kelvin to the Curie temperature. So we always have to look what is the application temperature to find the best material at that temperature. So what we are doing, we are improving the number of magnetic moments in the material, and we have to say that we are almost at the end of what theoretically is possible for ferrites in a technical sense. The second point is we, as already mentioned a few times, from the product point of view, the best way to increase the stability for DC currents is to introduce the gap or the multi-gaps even to reduce. So that's my daughter. I'm alone with her and she wants to tell me, sorry, but this is more or less what I wanted to say. I hope that answers the questions well. Thank you.
Okay, thank you, Dietmar. We will try to, since we already have 1 hour and we still have a lot of questions, try to go a little bit fast. Well, what are the consideration and effects of different material in switch mode inductor? Well, I think that the most important is the second part. Toroidal is better for MI.
I mean, for us, it is clear that we have different requirements in the market, and that is actually why we are having so many different materials. Yeah, and these different materials are, let's say, optimized to the requirements and parameters such as high BZAT, low loss, EMI suppression, and the switching frequency. So this is something which needs to be looked at. Really, what is the requirement and the need of the customer, and that is why we have these kind of sub-optimized materials available. For the second one, the biggest drawback we see in the market, as it is told by our customer base regarding toroid, is the difficulty of winding. So you need to wind directly on the toroid, and you need some sophisticated winding machines for doing this. While when you have a shaped core, you can use bobbins, much easier to be wound, and the reproducibility is much higher and better. So when you wind on a bobbin, the winding is almost the same every time, while winding on a toroid is much more tricky and different. I would say that is the biggest drawback for the toroid.
Okay, thank you very much again. That's one. Well, now we are going to start with the questions of that arrived just during the last 15 or 20 minutes. And In the meantime, I will launch the last survey. I promised you this is the last one. And while we are starting with the next question. How 3C95, 3C97, and CC98 compare in terms of price?
I have to say that we are not going to give euro per kilogram here because it is strongly depending on the size of the core. You can imagine that if you have a very small core, that the handling costs are much higher than the material cost itself. But to get an idea, between 3C95 and 3C97, I would roughly consider a 10% difference. And between 3C97 and 3C98, I would say it's almost the same price. But it is something you need to consider, as I said, also in terms of the volumes you are buying, as well as the custom, let's say the core shape and the size.
Thank you. Next question. Do the core material have the pass a high temperature shock test? I think that we have been talking about this in one of the first questions that Oscar said that, that was talking about shock, no?
Yes, I would say this, the way it is asked, I think it would be related to something like ACQ200 reliability tests. I have to say that, we in Ferroxcube, we have established our own aging test for ACQ200 reliability. And in general, ferrites are not very, ferrite cores don't suffer so much with aging on these high temperature, high shock conditions. It is more when you have the complete assembly, when you have glues, which are interfacing with the ferrites, and also copper windings, which can have different thermal coefficients.
Okay, thank you very much. Can you elaborate on ferromagnetic resonance?
This is for Dietmar, I think. Can you unmute him?
Okay. Just, sorry, 1 second. Dietmar, are you there?
Okay, now, thank you.
You're welcome.
Yeah, resonance is, of course, something which is not very well specified in the literature. There are different definitions, but somehow it's a point where the magnetic spins cannot follow anymore the frequency of the application. And yes, we are looking at it, and we are also specifically designing the material to increase the ferromagnetic resonance. So I don't understand exactly what is the idea behind the question. Yes, we look at it, we work on it, we improve it specifically.
Okay.
But, yeah, okay, thank you.
Thank you, Dietmar. What kind of material is best when the ambient temperature is below 0? Interesting.
Yeah, that depends, of course, also what kind of application it is. But we have not shown it today, but we are also looking especially for automotive customers on the low temperature behavior, typically from -40°C up to 150°C. And also here, there are differences in the materials and specific designs necessary to assure at low temperature best performance.
Most of the cases, -40° is very common in all of your materials, right?
The requirement comes from the customer, but typically we are showing in our material data sheets from -40, -50°C, the permeability curve.
Okay.
But we have already designed some materials which show better permeability at low temperature, but also kind of niche materials which we have not presented today.
Okay, thank you, Dietmar. is all of the data shown about material related to a specific shape? Yeah, I think that this question was answered by David. That they use a toroidal of 25 millimeter, right?
Yes,
Right.
we use a 25 millimeter toroid. Well, in the high frequency materials, we are using a T14, but for the rest, to specify the characteristics of the material, we use the T25, the toroid.
Okay, thank you. Well, I think that right now we didn't include any other question. My colleagues didn't include any other question. I suppose that the other questions that will be answered by email. I would like to thank you, all of you, for coming today, especially everyone that is from Ferroxcube in different places in the world. I mean, there's some in Germany, Poland, Spain, and of course, all the team from Frenetic that have been working very hard to create this seminar and prepare everything to everyone that it will be connected today. I mean, Pablo, Michael, Elisa, Mats, Barbara, and well, as I say at the beginning, we have two coming events. One is the Frenetic Live demo in the magnetic workshop. This is not, I think it's not for free, but it's going to be very interesting. If it is not for free, we will repeat later the same. And in the 16th of June, this is for free, a full bridge phase shift transformer design explanation at the PELS Association. Well, just thank you, all of you, for staying during more than, well, 1 hour and something connected today. It's been very interesting, at least for me, to see all the news from Ferroxcube and all the questions that the audience have made. I don't know if any Oscar or Hulk from Ferroxcube want to also say something just to close this webinar.
Yeah, I would like to say thanks to all who are interested in our products. And I would say we would like to point out that we are willing to support any customized idea. And we invite everybody to talk to you as Frenetic, as well as to us and to our technical people to make happen what is, let's say, demanded by the customers.
Okay, then this video will be online, and we also will share the slides later. Then, well, thank you all of you, and stay safe. Bye.
Bye-bye. Thank you.
Thank you.